everyone, I'm Xiao. I'm excited to present our work, Automated Expansion of Privacy Data Taxonomy for Compliant Data Breach Notification. The green, okay. In the privacy research domain, one of the biggest challenges is to comparing the specific data items used in the real-world application with the private data defined in the privacy laws regulations. And our previous study understands the legal professionals' practice and expectations in data breach incident reporting, which published in last year's CCS, revealed a significant gap between the legal professionals and the technicians in interpreting the data items. The main challenge here is the privacy laws are written by the legal professionals, which tends to use more broader and the more general terms like the PII, personal identifiable information, while the actual data usage practice handled by the developer tends to use more specific technical terminology. So there is a gap in between these two different people. And in our study, we refer to those data either defined in the privacy laws or regulations or those data used in the real-world application as restricted data. And a privacy data taxonomy is a structured solution to capture the relationship between the restricted data. So let's take a deep look at what is privacy data taxonomy. So it is essentially a structured hierarchy. It links the specific data items to broader and more general terms through the hyperlink relationships. As we can see, it can help us capture the relationship between the restricted data either by the data types like the location information, financial information, also by the level of granularity between restricted data, like the cost location. Cost location is the hyperlink of the precise location. So why it is important, as I mentioned before, it helps bridge the gap between the legal experts and the technicians in understanding the restricted data. However, building the privacy data taxonomy isn't easy because the restricted data item often diverse across different applications like mobile applications, IoT, or third-party library, SDK, etc. Second, the privacy definition usually broad, vague, and usually have different definitions across different laws. And the last, existing privacy taxonomy usually rely on the manual curation or the heuristic rules, which lack of the scalability when the new data types emerges or the privacy laws involves. Such static approaches fail to capture the dynamic feature in the privacy domain. So to address those challenges, we proposed an automatic method to recognize the restricted data and also integrate it into the privacy data taxonomy. So the key challenge here we address is to determine whether a data object has a hyperlink relationship with an existing restricted data category. For example, here, Wi-Fi position, we want to determine whether the Wi-Fi position has a hyperlink relationship with the course location. So in existing hyperlink prediction techniques in the open domain includes lexical pattern-based method, distributional representation-based method, and projection-based method. Those methods are effective in identifying the broad categories like the location information and the financial information. However, it failed to consider the granularity layers. For example, the structure to distinguish final granted granularity layers, like it cannot distinguish the course location and the precise location. Actually, they have the hyperlink relationships. So to address those challenges, we proposed a method called granularity-aware hyperlink prediction grasp to capture the granularity information from the taxonomy and to improve the accuracy of the hyperlink prediction. So in previous slides, as we can see in the privacy taxonomy, the upper layer restrict data usually are more broader and more abstract concept, while the lower level terms are more domain specific and more technical. And indicating that the granularity layer can be reflected from the privacy data taxonomy tree. However, we found that such features are neglected by the previously projection method. So because those kind of methods solely based on semantic similarity between terms, and which will mistakenly group the coarse location and precise location pairs into one cluster. Based on this observation, our method takes a step further by adding the relative position of the hyperlink on the taxonomy tree into measure the distance to classify the data pairs. So in our study, we will group the pairs with different granularity layers into different clusters and learn the projection matrix separately, ensure that the learned projection metric are granularity aware. So in the next few slides, I will just briefly introduce the high-level architecture of our method. It first will group different hyperlink pairs into different clusters based on the granularity layers, and at the same time, it also compute a set of attention weights based on the distance of the hyperlink pairs to the centers of each cluster. And then we will learn the projection matrix from the hyperlink to the hyperlink and aggregate the project offset from all clusters. And finally, we will apply the attention-based classifier to determine the existence of the hyperlink relationship in a candidate pair. So to evaluate the performance of our proposed method grasp, we curate the hyperlink pairs from two existing privacy data taxonomy. One is the privacy policy taxonomy, and another is IoT sensitive data taxonomy. And this slide shows the overall evaluation result of our method comparing with baseline models. And those baseline models include 4 naive methods and 2 state-of-the-art hyperlink discovery techniques, and also the large language model. And for the ChatGPT 3.5, we actually carefully refine the prompt and fine-tune the large language model using our training data set. But despite those efforts, the large language model didn't achieve the best performance, and probably due to their lack of the domain-specific knowledge. While our model grasp outperformed the baseline models across different evaluation metrics. So to demonstrate how the grasp can help the privacy professionals, we developed a tool called Tracy. A tool integrates the grasp into in helping the privacy professionals when they're analyzing those privacy reports or incident reports. So the Tracy will highlight the restricted data it recognizes, and at the same time, it will also show a subgraph of the privacy data taxonomy. As we can see, this subgraph visually connects the restricted data all the way to the restricted data defined in the GDPR, the privacy laws. We also recruit 15 privacy professionals, including legal experts and security experts, to evaluate the Tracy's ability to recognize privacy-sensitive data in the real-world incident report. And the results are very positive, and all of the participants agree that the Tracy achieved excellent traceability, which allowing them to trace the restricted data from the incident report back to the legal definitions in the privacy laws. And also it improved the efficiency for the privacy professionals in their daily life by reducing the assessment time. And also, most participants are willing to use the Tracy as a tool when they do the compliance analysis related task. So here is two takeaways. We designed and implemented a grasp for automatically constructing and expanding privacy data taxonomy, and we implement Tracy, a privacy professional assistant to recognize and interpret private data in the incident report for the GDPR compliant data breach notification. And we also put the SQL code for the code and data, and feel free to check it out. Thank you.
The speaker. We have plenty of time for questions. Yeah, please. Do you want to walk up on the mic? Thanks.
Okay. Thanks for talking. I have one question about the design of the tool. I mentioned. I remember that you use the k-means for the cluster, right? So you have a specific like k number for the cluster. How do you decide the k?
Yeah, that's a good question. So the k, this is a hyperparameter. So it's based on the taxonomy tree size. So if the taxonomy is huge, like the privacy policy domain, so the k will be larger. And if it is a more specific domain, like the IoT domain, the key will be relatively smaller.
Okay, so the key is predefined.
We also tested the sensitivity of the cluster to choose the best performance.
Okay, thanks.
Yeah, thank you.
Any other questions? Can I ask maybe one question?
Yeah, sure.
So, can you? I guess different regulations may have different definitions about some of those properties. Can your system adapt to those different legislations? Do you have to retrain for every jurisdiction, or? For the as I said, different taxonomy, different domain will have different taxonomy, and for the GDPR, you can see the root node is PII, while for the other nodes, if the high level nodes depend on the privacy data defined in the privacy laws. Actually, when we train the embedding model, we will pour over those documents and using those documents to train the embedding model, and then different terms in the specific domain will have different embeddings, and also different domain will have different privacy data taxonomy. Thank you.
Thank you for your talk, and I just have one quick question. So right now you build your taxonomy based on existing data, right? I'm curious about if that if you connect to the real world, if the new data comes, will that taxonomy update? And if it updated, will your approach can automatically update it with that?
Yes. So because this is purely automatic method, right? It of course can capture the dynamic landscape of the privacy domain, as I said before, when a new privacy laws evolves, and we can use in those documents and retrain our embedding model and to adjust the privacy update the privacy data taxonomy.
Okay, thank you.
All right, let's thank the speaker again.